Hello everybody, this is the biology exam review worksheet for grade 10 for the midterm exams at the International School of Innovation. This chapter is talking about the nervous system, nervous communication. It's about the organization of the nervous system in the vertebrates. What is the function of the nervous system? Mainly the function of the nervous system is to receive information, to process information, and to respond to this information. The central nervous system is composed mainly of two parts, the central and the peripheral nervous system. Here we have spinal cord, brain, and we have the nerves. Central general nervous system of a vertebrate. It includes mainly cerebrum, cerebellum, medulla oblongata, and we have the spinal cord. Cerebrum, cerebellum, and the medulla oblongata, they represent something known by the brain. Here we have a structure in brain or the encephalon, the frontal lobe, the temporal lobe. Cerebrum is composed of two hemispheres, the right cerebrum and the left cerebrum. We have the cerebellum here, and here we have the medulla oblongata. Finally, we reach to find the spinal cord. Nervous system is composed mainly of two parts, as we said, the central nervous system and the peripheral nervous system. Mainly the central nervous system is composed of the brain and the spinal cord, while the peripheral is composed of the cranial nerves and the spinal nerves. Cranial nerve, they come from the cranium. Brain is composed of cerebrum, cerebellum, and medulla oblongata, as we said before. And the cranial nerves, they ramify from the brain. Spinal nerves, they ramify from the spinal cord. Here we have the brain, which includes the cerebrum, cerebellum, and the medulla oblongata. What's the function of these three parts? Is to analyze received information, integrate them, and then you have to take the proper decision. While function of the cranial nerves and the spinal nerves, cranial nerve, they ramify or they branch from the brain. Spinal nerve, they ramify from the spinal cord. They carry messages between the CNS, central nervous system, and the effector organ or the receptor organs. So nervous system is composed of two parts. One, central nervous system. Two, the peripheral nervous system. Central nervous system composed of brain and spinal cord. Brain is composed of three parts, cerebrum, cerebellum, and the medulla oblongata. Why? The peripheral nervous system composed of cranial nerves and the spinal nerves. Cranial nerve, they ramify from the brain. Spinal nerve, from its name, they ramify from the spinal cord. They carry message between the central nervous system and the effector organs. Here we have the nervous system is a network that includes, what does it include? Includes stimulus. First, we have the receptor organ. Second, we have CNS, central nervous system. And finally, we have this, the effector organ, and to reach to the action. So first of all, we need the stimulus. For example, heat. This is a stimulus. Receptor organ, I hold a hot cup of tea. The stimulus is the hot cup. The receptor organ is my hand. The receptor organ sends the message to the central nervous system. The central nervous system sends the message back to the effector organ. It's so fast. The effector organ takes an action to hold my hand, for example, or remove my hand from the cup. First, our receptor organ, it recognizes the stimulus and stimulate a message. My hand, it recognizes that this cup is so hot, you have to do something for this. Second, we have a sensory pathway between the receptor and the central nervous system. It's called the sensory neuron, or it has another name, is afferent. It conducts a message from the sensory organ, which is the receptor organ, toward the central nervous system. Second, we have the central nervous system. It receives information, analyze them, and integrate them, and decide the proper action, and send this action toward the effector organ using a motor neuron. So in the middle here we have sensory neuron, And here in the middle we have something called motor neuron. So motor neuron, it conducts a message from the central nervous system to induce a response toward the effector organ, which has to induce the response or the action. This is by the help of the motor neuron, which is called efferent. So sensory neuron between receptor and the central nervous system. Between the central nervous system and the effector, we have a motor neuron, which is called efferent neuron. And finally, the effector organ, it receives the decision to perform an action or to stop an action. This is the figure. Receptor organ, they recognize the stimulus and simulate a message. Between the receptor organ and the central nervous system, we have a sensory neuron. It's called afferent. Conduct a message from the receptor organ or the sensory organ toward the central nervous system. Central nervous system receive information, analyze, and integrate them toward the motor neuron by the help of a motor neuron. Motor neuron is efferent, which conduct a message between the central nervous system and the effector organ. So between receptor and central nervous system, it's a sensory neuron. It's called afferent. While between the central nervous system and the effector organ, we have motor neuron, which is called efferent, to have the action finally. This is the figure of the spinal cord. Here we have, for example, I may give you this figure in the exam. You have to label it white matter, and this one is called the gray matter. We have the motor neuron, monosynaptic synapse. We're going to talk about this later. So this figure shows the spinal cord. We have the white matter, as I said. Here we have the gray matter. Here we have the dorsal fissure, dorsal root, the ventral root, and here we have the ventral fissure. And then in the middle we have the cerebrospinal canal. Here, as I said, here we have the sensory input, send the message to the brain, integrate, analysis, and through the motor neuron, which is called efferent, toward the effector organ to take an action. So we have, I saw a cup of water, I saw it using my eyes, through the sensory neuron, toward the central nervous system, they are called afferent, toward the central nervous system, and using the motor neuron, which are efferent neuron, toward the muscles of the hand to take an action where the hand approach. So stimulus, receptor organ, sensory neuron, central nervous system, meaning the interneuron, motor neuron, effector organ, and finally the response or the action. So this is the pathway of the nervous message. It moves stimulus, receptor organ, sensory neuron, central nervous system, motor neuron, effector organ, and finally to reach to the response or to the action. R sim reflex arc pathway. First we have R, which is receptor neuron, they receive the stimulus. Second, S, first R. Here we have S, which is sensory neuron, they pass the impulse on. I, it's called the interneuron between the sensory and the motor, and the spinal cord processes. And finally we have the M, which is the motor neuron which have to act. It is the R sim reflex. Anatomy of a neuron. A neuron, as we know, is typically made up of dendrites, cell body, which is called the soma, which contains the nucleus, and we have the axon, which may or may not be covered by myelin sheath. Finally, we have the terminal arborization, which is called the terminal buds or knobs. So dendrites, cell body, axon. Cell body is called the soma, which contains the nucleus, dendrites, cell body, axon, and finally we have the terminal arborization here. So this is dendrites. Here we have cell body, which contains the nucleus. This is cell body, it's called the soma. Some neurons, they are myelinated, they contain myelin. This is the axon. And finally we have the synaptic terminal or terminal arborization. So the neuron is the basic structure unit of the nervous system. Dendrites, they carry impulses toward the cell body. They carry the nervous message toward the cell body. And axon, they carries impulse away from the cell. We have myelin sheath. We have synaptic terminals. They contain mainly epinephrine, norepinephrine, acetylcholine, or GABA. We're going to talk about this later. So The structure and the functional unit of the nervous system is the nerve cell, or it's called the neuron. A neuron is referred to be as a bundle of nerve fibers. A nerve is a bundle of neurons. So a group of nerve fibers, they give a neuron. Group of neurons, it gives a nerve. Group of nerves, they give the nervous system. Nerve fibers, group of them, they give a neuron. Group of neurons, they give a nerve. And group of nerves, they give a whole nervous system. Neurons can be classified following two criteria, either their structure or their function. Classification according to their structure is classified into three kinds. First one is called a unipolar. It's called a T-shape. It looks like a T-shaped neuron. This type of neuron is found in the sensory neurons of the spinal cord, containing one axon, one dendrite, and they are directly joined. Second, we have the bipolar. Bipolar is found meaning it's the retina of the eye and the cerebellum, contain one axon and one dendrite. They are joined through the soma. It's called bipolar. And finally, we have the multipolar. Multipolar neuron is mainly found in the cerebral cortex, retina, and the spinal cord. It shows many dendrites, as shown here. It shows many dendrites and only one axon which leaves the cell body. According to their function, we have three types. As I said before, we have sensory neurons called the afferent, receive and conduct sensory information from the peripheral sensory organ toward the CNS, which is the central nervous system. Associative neuron is called the interneuron. It receives nervous message from the sensory neuron, integrated, and then carry or conducts nervous message toward the motor neurons. Look like a link between the sensory and the motor. Mainly it's found in the brain or the spinal cord only. Motor neuron is an efferent neuron. It carries nervous messages away from the central nervous system toward affected organ like the gland, the muscle, to induce a response there. This is a figure that shows a brain in the skin, how does it use an action and a response. Here we have the stimulation here at this level. We have stimulation. It moves through the sensory neuron, afferent neuron, toward the brain, and then the brain sends the message back. Here, the brain sends the message back to afferent neuron toward the organ to take an action. What is the role of myelin? Myelin shaft is a lipoprotein. It's the definition of myelin shaft. It acts as a protective layer of the axon and as an insulator. Myelin shaft is not continuous along the axon. The gaps are known by nodes of Flaherty. Actions, maybe, they are classified into two types. We have something known by voluntary and involuntary. Voluntary actions, actions that require thinking, actions that require the intervention of the brain in addition to the spinal cord. While involuntary actions, they are reflexes, they do not require thinking, actions do not require the intervention of the brain. Is a neuron always active? This is the big question. Are we always listening? Do you think that you always listen? Are we always walking? Are we always in pain? No. Sure no. So, what is the big answer? Do you always think? Mostly you don't think. Mostly, sometimes you have to stop thinking. So the neuron or nerve fiber is said to be at rest in the absence of a stimulation. If there is no stimulation, so there is no action of a neuron. Aim of the following experiments is to study the electrical state of a neuron at rest. Here we have recording of action potential. Recordings are obtained on a giant axon of a neuron by using microelectrodes connected to a galvanometer or an oscilloscope mainly. Here we have experiment number 1. We have nerve fiber, axon, and here we have physiological solution. And here we have the oscilloscope. The needle of the voltmeter, didn't deviate from 0. What does this imply? It remains at 0. This indicates that there is no potential difference between across the surface of the axon, or there is no potential at all. at the surface of the atom. Whenever it negates 0, so there is no action potential. Moving to experiment number 2. The needle of the voltmeter didn't deviate from 0. What does this indicate? There is no potential in the internal medium of the atom. Both of the electrodes, they are connected to the internal, so there is no difference, so no potential difference. Moving to experiment 3. Experiment 3. One of the electrodes is outside, other is in the internal part of the axle. So the needle of the voltmeter deviated away from 0 and the graph indicates minus 70 millivolt. So delta V, what can you deduce? What may be deduced from these experiments is as follows. In urine at rest, there exists a potential difference between the interior and the exterior of the nerve fiber. Between the interior and exterior, not between the exterior only and not between the interior only. Between the interior and the exterior of the nerve fiber. Between the interior and the exterior of the nerve fiber. So delta V is less than 0, which is minus 70 millivolts. So the interior of the nerve fiber is negatively charged with respect to the exterior. The resting potential is the potential difference that exists between the intracellular and the extracellular, between the interior and the exterior of media of a nerve fiber that is at rest. So the resting potential is the potential difference that exists between the intracellular inside and the extracellular outside media of a nerve that is at rest. This is the figure, interior, and this is the exterior. This is plasma membrane, and this is microelectrodes inside the cell. And here the microelectrode is outside the axis. Okay, the resting potential. What is this meaning? What is the membrane potential? And what the meaning of resting potential? There is an electric charge across the membrane. This is the membrane potential. Whenever you have electric charge across the membrane, it's called membrane potential. The resting potential, when the cell is not firing, is at rest, is 70 millivolt. Delta V is equal to minus 70 millivolt between the inside and the outside. So the resting potential of a neuron, you have to know this, it's minus 70 millivolt. Resting potential, all cells, not just excitable cells, they have resting potential and related to charge across the plasma membrane. The size varies between the cell, but it runs about minus 70 millivolt. Here, you have to know the note that the resting potential may range between minus 5, to 90, minus 90, depending on the species and the nature of the nerve. Here we have 3 Na+, you are picked up, 3 Na+ are picked, and they pump to the extracellular fluid, and 2K+ you are picked up. So the 3 goes out of the cell and 2K+ they enter the cell. Then the 2K+ are pumped inside the cytosol. How is resting potential maintained? At rest, sodium gates are closed. Na+ gates they are closed. The brain is 50 times more permeable to K+ potassium ions, causing them to leak out. This causes the outside of the brain to have an abundance of positive charge compared to the inside. The inside of the membrane is negative compared to the outside. Sodium potassium pump, Na+, K+ pump, allows K+ ions in for Na+ to go out where 3 Na+ goes out. This further creates a charge difference. But is in urine always at rest? Some notes you have to keep in mind here. What the meaning of an excitable urine? An urine that's able to respond to an effective stimulus, this is called an excitable urine. What the meaning of an action potential? Is term given to the electric visualization of the response of a urine. It's called action potential. First, excitable urine, and second, we have definition of action potential. You have to keep in mind also what is the meaning of threshold of excitation. Threshold of excitation if the minimum intensity of a stimulus is able to stimulate a receptor that may or may not emit a nervous impulse or message. Below this intensity of stimulus, no response will be recorded. Now we have to know that upon excitation, a change in the potential difference across the interior and the exterior of the nerve fiber should occur and reach a threshold of depolarization in order to initiate an action potential, which means a response. Threshold of depolarization is the minimum change in the potential difference that should be reached in the nerve fiber so as to create an action potential. Also, you have to keep in mind these notes: minimum time of excitation, the minimum time during which an effective stimulus should be applied in order to excite failure. This is some experiments are done. At rest, it's minus 70 millivolt. This is the resting potential. No change in the potential difference upon stimulation or stimulus of intensity I1, which is less than the threshold of excitation. So no change in the potential difference between where I1 is less than the threshold of excitation, no change in the potential difference, as if nothing is occurred, no action potential is stimulating this nerve fiber. This stimulus is said to be ineffective since it doesn't cause any action potential. Moving upon application of stimulus I2, less than threshold, but you have to say that I2 is greater than I1. You have small artifact here, small action potential, not considered as action potential, artifact. So this is reaching the threshold of depolarization, doesn't reach this. So slight change in the potential difference, slight depolarization, doesn't reach the depolarization. Slight depolarization is called artifact that did not reach the threshold of depolarization. Then everything goes back to the normal situation. This stimulus is said to be ineffective. 3. Upon application of stimulus of intensity I3. I3 is greater than or equal to the threshold of excitation. As sure, I3 is greater than I2, so we have small artifact and we have an action potential here. This is the action potential that I'm talking about. So I3 is greater than or equal to threshold of excitation, and enough change in the potential difference occurs that reaches the threshold of depolarization. An action potential of amplitude about 120 millivolt was recorded. This simulation is said to be effective, and it's called the threshold of excitation. While I4 is greater than or equal to the threshold of excitation, also an action potential is recorded. As enough change in the potential difference occurs that reaches the threshold of depolarization, the same response was recorded, so the stimulus is also effective. Here we have action potential in nerve fiber. We have different stages: 1, 2, 3, as named here, 4, 5, 6, these stages, and finally 7. What do we call each stage? 1, it's called the resting potential. 1 is called the resting. High popularization or artifact, whenever we have a small high popularization, it's called the artifact. Depolarization, whenever it reaches toward the action. Inversion of polarity, whenever it goes back like this. Repolarization, hyperpolarization, and finally we have to go to the resting potential. This is stage number 7. Here we have some phases of the action potential. 1. Electric interpretation of the difference. Depolarization. What happens? It corresponds to the hypopolarization of 120 millivolt. We have 50 minus 70. It's 50 plus 70, so it's 120. This indicates that the interior becomes more positively compared with the exterior, which should become more negative. Repolarization, when it comes back to minus, which corresponds to the feedback to the initial stage. This potential difference drops from 50 millivolt to reach minus 70. This indicates that the nerve fiber is once again more negatively on the interior with respect to the exterior, which become more positively charged. 6. Hypopolarization. Hyperpolarization corresponds to the increase in the electronegativity of the interior of the nerve fiber, where delta V drops to about minus 70 millivolt. This indicates that the interior is now more negative compared to the resting state. Now we're going to move to the understanding the ionic changes. Resting phase. This state the cell is highly membrane to K plus than to Na plus, where more K plus on the inside and more Na plus on the outside. Once continuing with the ionic interpretation, depolarization, the membrane permeability to Na plus is more permeable to Na plus where it increases, and the permeability to K plus decreases. It's become more electropositive. This before depolarization, more positively charged in the outside, more negatively in the inside. This figure rapid depolarization where more positive enters inside the cell and the delta V will increase. This is the action potential and the nerve, the threshold potential resting about minus 70, and whenever we have this speed it's called an action potential. So threshold potential will trigger an action potential or a nerve impulse. We're gonna have an action potential or a nerve impulse. So the action potential is an all or none. So be the law of all or none. Moving back to the ionic interpretation of the repolarization, the anterior where it becomes more electronegative. Repolarization phase, the sodium ion channels they close and become refractory. Depolarization trigger opening of voltage gated potassium ion channel. This K plus rush out of the cell, repolarizing and then hyperpolarizing the membrane. This is the repolarization when it comes back toward the negativity. Finally, we have the hyperpolarization. K plus channels are still opening. We are too slow to close. So more positive accumulate on the outside of the fiber as compared to the resting. The interior becomes more electronegative than the resting phase. Resuming the resting potential, potassium channels they close. Repolarization reset sodium ion channels. Ions diffuse away from the area, and the sodium potassium Na plus K plus transporters maintain polarization. The membrane is now ready to fire again. All or none response. If an action is simulated above its threshold, it will trigger an impulse down its length. The strength of the response is not dependent upon the stimulus. An action cannot send a mild or strong response. Either it sends or it doesn't. Either it responds or does not respond. Why does the nervous message always propagate unidirectionally? When a zone of nerve fiber is excited efficiently, depolarization occurs and an action potential is created. This depolarization, it will create or stimulate the depolarization of the nerve zone ahead. This is because the previous zone is said to be in a refractory period, non-excitable one. As such, the nervous message propagates forward and never backward in vivo. So therefore, the nervous message is said to propagate in a unidirectional manner from dendrite cell body toward the axon and to the next cell. How to measure the speed of propagation of the nervous message? How to measure the speed of propagation of nervous message? Here we have a stimulating electrode and we have a recording electrode. This is delta D, the distance between these two electrodes, and we have delta T is the time between each response. So V, as you know, is equal to delta D over delta T. reciprocal distance over the time as in the physics. Factors that affect the speed of propagation. First, the diameter. So we have D1, D2. As you see here, D1, nerve fiber 1, D2, nerve fiber 2. As we all see that D2 is greater than D1, so the nervous message propagates faster whenever we have a larger diameter. So V1 is greater than or less than, since it has less diameter, so D2 has the highest diameter, the greater diameter has the greater velocity. So diameter of the nerve fiber affects, as the diameter of the nerve fiber increases, the speed of the nervous message increases also, where as D increases diameter, the speed of propagation of the nervous message increases. Second factor, myelination of the nerve fiber. Nerve fiber 1, nerve fiber 2. Nerve fiber 1 is not myelinated, nerve fiber 2 is myelinated. So in the nerve fiber 2, the speed is more than the speed in the nerve fiber 1. What does this mean? Presence of a myelin has a higher effect on the increasing of the speed than the effect of the diameter. What does the myelin do for the propagation of the nervous message? In the absence of a myelin in a non-myelinated nerve fiber, the message propagates by this way. While whenever we have a myelin, the message propagates in a myelinated fiber in a such way it's called a saltatory movement. Myelin is an insulator. It doesn't conduct a nervous message, so it doesn't conduct. You have to jump over this. If you see here, it's jumping. 1, 2, 3, 4. The jumping movement, as you see here, the propagation of the message is like this way. This is called a saltatory movement or saltatory manner. The message propagates in saltatory movement, so it's going to be a faster one. Saltatory conduction. The jumping of an impulse between the nodes of round V, thus dramatically increasing its speed. It only occurs in the case of the presence of myelin, 2 meters per second to reach 120 meters per second. Factors that affect the speed, also we have temperature. T1 equal 20, T2 equal 30 degrees Celsius, nerve fiber 1, nerve fiber 2. T1 is less than T2. That means that T2 is going to be the strongest one and will have the strongest velocity. V2 is greater than V1. So as the temperature of a nerve fiber increases, the speed of propagation of the nervous message will increase. Third factor is drugs. Drugs, we have two types. We have drugs that are stimulants. We have other they are tranquilizers. Stimulants, they stimulate the message. Why? The tranquilizers decelerate the nervous message. Now we're going to move to the worksheet, exam review worksheet. We're going to start solving this. Indicate the true statements and correct the false one. A nerve is a bundle of neurons. Sure, this is true. According to the structure, neurons are classified as sensory, interneuron, and motor. This is not according to structure, this is according to function. Or if you want to say according to structure, neurons are classified as unipolar, bipolar, or multipolar. This is false. Resting neuron is the neuron that's able to respond to an effect. No, this is called an excited neuron. Resting phase of the action potential, the cell membrane is more permeable to keep plants than a plant. This is true. And finally, we have the threshold potential will trigger an action potential on nerve input. This is true. So false according to the structure. Number 2B. Neurons are classified unipolar, multipolar, or bipolar neurons, or according to their function, they are classified as sensory, interneuron, or motor unit. Question number 2 says, we subject a nerve to a series of electric excitations of increasing intensity I1, I2, I3. I1, I2, I3, and I9, reaching I9. These are increasing intensity for I1 less than I2 less than I3. The amplitudes are listed in the table below. Intensity, and we have the amplitude. Construct the curve. You have to construct the curve. This is intensity, and we have the amplitude. Again, the shape of the curve will be like this and reach a threshold values. So analyze the obtained graph. As we increase I1 and I2, there is no amplitude, there is no action potential. So I1 and I2, they are classified as ineffective stimulation. The first one to have a stimulation is I3, so it's classified mainly as the threshold of excitation. So first I1 and I2, you have to say after applying stimulation of intensities I1 and I2 to the nerve, no action potential was recorded, was 0 millivolt. Then, the first action potential were recorded at I3 with an amplitude of 110 millivolts. So as the intensity increases from I3 to reach I7, the amplitude increased reached 680 millivolts at I7 and it stays constant at I8, I9. Effective, ineffective, so they are I2, I1, and I2. Effective stimulations, they are all of them I4, 5, 6, 7, 8, and 9. The threshold of excitation, sure is where the first action potential was recorded, so it's I3. Do we obtain the same result if we replace the nerve by a nerve fiber? Justify your answer. First, you have to go to the graph analysis. After applying the simulations of intensities I1, I2, and I3, no action potential was recorded, which is 0 millivolt. The first action potential was recorded on I3 of amplitude 110. As the intensity of stimulation increases from I3 to I7, the amplitude of response increases to reach 680 millivolt and it remains constant as the intensity increases from I7 to I9. This is the analysis. 3. There is no action potential recorded at intensity I1 and I2. They are ineffective. The first action potential was recorded where at the intensity I3. So this is the threshold of excitation. Since we have the first action potential, I4, I5, I6, I7, I8, and I9 shows action potential. So they are effective stimulation. If we replace the nerve by nerve fiber, justify the answer. What will happen? Do we have the same results? Sure, no. Does the nerve fiber obey the law of all or none? Why? The nerve fiber doesn't obey, the nerve doesn't obey this rule. So the nerve fiber obeys the law of all or none, which means that either you observe an action potential or you didn't observe an action potential. Question number 3. Pacini corpuscles are mechanoreceptors of the skin. They are sensitive to pressure. By the help of the device represented in document 1, we exert pressures of increasing intensities, and we register the potential that appear on the nerve fiber when in contact with the corpuscle in document 2. Analyze the registration of document 2. What can you conclude concerning the coding of the intensity of the stimulus? Identify the threshold of excitation. Here we have this figure. We have the system permitting the application of pressure. We have the fiber body, nerve coding, this is the Pacini corpuscles, this is the nerve fiber, electrodes, and the physiology information. Here we have the beginning of stimulus of a pressure 0.2 gram per centimeter square. Here 0.5 gram per centimeter square, 4 gram per centimeter square, and 30. If you see here at 0.2, we didn't see any actual potential. It starts about 0.5 gram per centimeter square. So the first action potentials, they are the same amplitude, but they differ in the frequency. So for pressure of 0.2 gram per centimeter square, no response was recorded. As pressure increases to reach 13 gram per centimeter square, the number of recorded action potential increased to reach about 45 action potentials of same amplitude within the given time. Since as the intensity of stimulation increases, the number of the recorded action potential increases, but keeping the same amplitude. The amplitude doesn't change. Then the nervous message is coded by the frequency and not by the amplitude. Part B, identify the threshold of excitation. Since for I equals 0.2 gram per centimeter square, no response was recorded, And for I equals 0.5 gram per centimeter square, the first time this experiment few action potentials were recorded, then the threshold exists between these two, between 0.2 and between 0.5. It's greater than 0.2, but yet it's less than or equal to 0.5 gram per centimeter cube. So the nervous message here is coded by frequency of null by amplitude, and you have to know the amplitude is the same but the frequency is different. Pay attention to these notes, study well guys, and good luck for your exam. Bye bye.
If you want to connect between two people, we need a landline phone. So what's about the connection between two neurons? What do we need to connect neuron number 1 to neuron number 2? We need something called a synapse. What is synapse? We are going to talk about synapse. So here the big question is, how does nervous message propagate from one neuron to the following cell? What do this nervous message need to move from one medium or from one neuron to the following cell? This needs something done by a synapse. What is the synapse? It's the functional connection between the neuron and the following cell, maybe another neuron, a gland cell, or a muscle cell. We have the structure of the synapse. We have a presynaptic neuron, which is before the synapse. This is the presynaptic neuron. We have the postsynaptic neuron, which follows the synapse. And in the middle, we have something known by the synaptic cleft. This shows the density of synaptics and density between persons at birth, 6 years old and 14 years old, and these figures show the difference related to the synaptic density. Classification of synapses. Synapses, they are classified either according to their structure or according to their function. Classification of synapse, maybe in neuronal synapse, in neuromuscular synapse, or in neuroglandular synapse. Neuroglandular, they are called, both of them, they are called neurofactor synapse. Classification. According to structure, we have neuronal and neurofactor synapse. Neuronal synapse is between two neurons, while neurofactor synapse is between a neuron and an effector. Neuronal synapse, this figure shows the different neuronal synapses. To start, neuronal synapse, first we have something known by the neuronal synapse. The first type is called axodendritic synapse. It's between an axon and a dendrite, as shown in this figure. It's called axodendritic synapse. Second, we have between an axon and a soma. It's called axosomatic synapse. And third type, which is the last one in neuronal, between the axon and another axon, is called axonal synapse. Now we move to something called the neuroeffector synapse. Neuroeffector synapse, it's the synapse between a neuron and a muscle. It's called neuromuscular synapse. It has another name, motor and plate. And we have another type, neuroglandular synapse, between a neuron and a gland. Example here, it's about the adrenal gland. Classification of synapses according to neuroeffector. Either we have neuromuscular synapse, it's called motor and the plate, or neuroglandular synapse between a gland and a neuron. According to their function, we have two types. Either it's excitatory synapse or it's an inhibitory synapse. Excitatory synapses. What is the function of the excitatory? They allow or they permit the propagation of the nervous message from a presynaptic neuron toward the postsynaptic cell. They allow or they permit. That's why they are called excitatory. While the opposite is true here. The inhibitory synapses, they inhibit or they prevent or they stop or they block the propagation of a nervous message from a presynaptic neuron toward a postsynaptic cell. Details of the synapse itself. Maybe in the exam I'm going to give you this figure. I told you label this figure. This circle represents the synaptic vesicle that contains neurotransmitter. We're going to take the definition of neurotransmitter later. Example about these neurotransmitters. They are acetylcholine, dopamine, and others. Here we have the presynaptic membrane, the presynaptic cell, or the presynaptic neuron. In the middle we have the synaptic cleft. These are the binding sites for them. And these are the postsynaptic membrane that includes the channels, Na+ channels, calcium channels, and others. Propagation of a nervous message through a synapse. First, let's say what is a neurotransmitter. A neurotransmitter is the chemical mediator between two synaptic cells. It is released by the presynaptic neuron into the synaptic cleft, where it binds to the specific receptors on the membrane of the postsynaptic cell. So to repeat, neurotransmitter is a chemical mediator between two synaptic cells. First, it's released by the presynaptic neuron into the synaptic cleft, where it binds to specific receptors where they are found on the post. So it's released by the pre and the synaptic cleft and bind to receptors on the post. First, the nervous impulse reaches the presynaptic terminal buds, causing a depolarization. This depolarization opens the voltage-gated calcium channels, Ca2+ channels, where Ca2+ rushes into the presynaptic buds. Then the secretory vesicles will be mobilized toward the cell membrane of the bud and they bind to it. Then the vesicles release the neurotransmitter into the synaptic cleft by a process called exocytosis. These neurotransmitters will bind to their specific receptors, as we said, on the postsynaptic cell. Moving to the step 6, 7. If the synapse is excitatory synapse. If the synapse is an excitatory one, what happens? The neurotransmitter will bind to a chemically gated, ligand-gated Na+ channel. As such, Na+ channel sodium channels will open. Na+ ions flows into the postsynaptic cell, causing depolarization. What we have now something called by EPSP. E, excitatory, P, post, S, synaptic, P, potential. EPSP, excitatory postsynaptic potential. To continue here, if this depolarization exceeds the threshold of depolarization, then an action potential will be fired. This if the synapse is an excitatory synapse. Now we move to the propagation of the nervous message through a synapse if the synapse is an inhibitory one. If the synapse is an inhibitory one, due to this hyperpolarization, no response will be recorded in the postsynaptic cell. As well, no response in both synapses. In order to not to exhaust the postsynaptic cell, the neurotransmitter will be degraded by enzymes found in the synaptic cleft, or it may be recaptured or its reuptake by the presynaptic terminal. Propagation of the nervous message through a synapse. We have state of a convergence. Convergence apply the same here. The state of convergence. State of convergence, we have the many presynaptic neurons. They carry nervous messages to one postsynaptic cell. Example about this, the interneuron inside the brain. This is the state of convergence, while the other state is the state of divergence. The meaning of divergence, state of divergence, it's when one presynaptic neuron carries nervous messages to many postsynaptic cells. Now we move to the drugs mode of action. Drugs mode of action. Either the drugs is an endogenous chemical, endogenous meaning that it is produced or found naturally in the body like hormone, neurotransmitter, or it may be an exogenous chemical, meaning that it's an artificial one that is provided from external sources into my body. Example, drugs, medicines, and others. Also, we are talking about drugs. We have something called agonistic drug, antagonistic drug. What is the agonistic and what is the antagonistic? Agonistic drug. Agonistic, if the drug had the same function or effect of an endogenous neurotransmitter, or at least it enhances its function or facilitates its function. While antagonistic is the opposite of agonistic. Antagonistic drug, if the drug has opposite function or effect of an endogenous neurotransmitter, or at least inhibits or blocks its function. We have analgesic and analgesic substance. Analgesic, it causes pain, like the pain substance, and analgesic, it reduces or relieves the feeling of pain. Example about this, morphine. Mode of action of amphetamines on dopamine synapses. In normal cases, dopamine is released in few amounts, causing a limit in pleasure and hyperactivity feeling, which ends after a short time. Amphetamine. How does amphetamine work? Amphetamines, as well as most ecstasy drugs, they facilitate or activate the exocytosis of dopamine. This play a role in controlling body movement, thus increasing activity, prolonging the feeling of pleasure. So these two drugs, dopamine is an endogenous one and neurotransmitter, and amphetamine is an exogenous. Both of them, they have the same function, the same role, where amphetamine facilitates exocytosis, meaning that they are agonistic. Mode of action of morphine and the pain circuit. Usually there are three neurons that interfere in the transmission of a pain message and thus in the pain sensation. One is called a modulatory neuron that secretes enkephalin. Enkephalin is known as endorphin as a neurotransmitter. The presynaptic neuron that secretes the P substance that we said before is called P substance as a neurotransmitter. 3. The postsynaptic neuron, the one that possesses specific receptors for the P substance. Mode of action of morphine and the pain circuit. In normal cases, enkephalin is released and binds to specific receptors on the presynaptic neuron. This will decrease the exocytosis of the P substance. This partially inhibits the pain message and thus the feeling of pain. While morphine and enkephalin, they have highly similar spatial configuration, meaning that they have highly similar shape. Thus, morphine binds to the receptors of the enkephalin on the presynaptic neuron and totally blocks the exocytosis of the P substance, so no more P substance. This is called complete inhibition of P exocytosis. This leads to the total inhibition of the pain sensation. These two, they are agonistic. How binding sites work, how do they work with each other, what facilitates the binding, and so on. Neurotransmitter reuptake helped keeping binding sites clear. Now guys, we're gonna move to the mode of action of cocaine on dopamine synapses. In normal cases, dopamine is released for a few seconds, giving the person the pleasure feeling, as we said before, for a short time, after which dopamine is reabsorbed or recaptured into the presynaptic neuron. Here, we're going to take the function or the mode of action of cocaine. Cocaine blocks the recapture of dopamine, which prolongs its activity, its effect, allowing longer fixation on its receptors on the postsynaptic membrane. This will prolong the feeling of pleasure. So this, no more recapture. Cocaine blocks this property. As we said, dopamine is an endogenous, while the cocaine is exogenous, and they have agonistic function, dopamine and cocaine. Cocaine inhibits the reuptake of dopamine, producing effects such as increased heart rate and increased blood pressure. So this shows the inhibition of the reuptake. How do you explain the mode of action of cocaine? First, it binds to channels on the presynaptic membrane and prevents the dopamine recapture by the presynaptic neuron. Second, action of dopamine persists as long as dopamine is binding to its receptors. Cocaine acts agonistic to dopamine. They have the same function, or at least enhances the function. And cocaine thus acts on the presynaptic membrane. Normal dopaminergic synapse. Arrival of the action potential toward the presynaptic terminal. 2. Calcium penetrate presynaptic node. 3. The dopamine neurotransmitter is released. Dopamine binds to the postsynaptic membrane receptors. And number 5, we have the pleasure occurs. Recapture of dopamine through channels on the presynaptic membrane should occur. Action of cocaine on dopaminergic synapse. First, in presence of cocaine, arrival of action potential, Ca2 plus penetrate presynaptic node, and we have the release of dopamine, binding of dopamine to postsynaptic membrane receptors, no recapture of dopamine by the presynaptic neuron, and the pleasure feeling is prolonged and persists. This figure shows how do the action potential move. First, we have the action potential received is arrived toward the presynaptic. Then we have the calcium, they enter inside the presynaptic neuron. Then we have the release inside the dopaminergic receptors. They move, they cause something going by the pleasure or feeling of pleasure. Mode of action of Curer on acetylcholine synapses. How do they work? In normal cases, acetylcholine is an excitatory neurotransmitter in the motor end plate, mainly in the skeletal muscles, leading to their contraction. So, Curer and acetylcholine, they have highly similar spatial configuration, special shape. Thus, Curer binds to the receptors of the acetylcholine on the postsynaptic neuron, preventing the binding of acetylcholine. This leads to the muscle relaxation and or even paralysis. So these two, first acetylcholine is an endogenous, while Curer is exogenous substance, and both of them they have an antagonistic function. They are antagonistic, they have opposite functions, or minimum they inhibit their function. Curer inhibits. So nicotine, all of you know about nicotine. Nicotine fills and activates acetylcholine binding sites, producing effects such as increased heart rate and increased blood pressure. This is the function mainly of nicotine. And be careful, concentrate on the action of the acetylcholine and Curer. Be careful for this. Maybe you're gonna have this question in the exam. Good luck, guys. Bye bye.